Okay, can I start? Yeah. All right. So, hello everyone. Today I'm going to talk about something about operator algebras and convexity. I mean, we all know that whenever functional analysis and convexity, the notion of convexity comes together, it gives a very beautiful theory. So today we are going to discuss various operator algebras, and then I want to motivate how convexity come to the picture uh, when I'm talking about my research or my work. Okay, uh, uh, convexity can come into the picture from various directions, but I will mostly be concentrating on my work. So, yeah. All right. So, I'm assuming that not everyone took the course of operator algebras in our and math. So maybe I give I would like to give a brief description of what are these objects are. So C-star algebra, I want to define C-star algebra. So before that, uh, right. So before that, let us define what is Banach algebra. So a Banach algebra is a non-vector space. So basically, it is a vector space. It has some norm in it, and it also has some vector multiplication. Okay, so basically you can multiply two vectors to get another vector. Okay, and this multiplication is very good with the vector space structure. So for example, it is distributive. Firstly, it is distributive. That means if x is multiplied with y plus z, then it will give you xy plus xz, and similarly so on. Second point is the multiplication is sort of continuous. Yeah. So norm of xy is less or equals to norm of x times norm of y for all xy in the Banach algebra A. And with respect to this norm, uh, the vector space is complete. Okay. Yeah. Then I want to define what is C-star algebra. Okay. C-star algebras are basically a class of Banach algebras with some additional structures. Okay. Now here, firstly, it has to be a Banach algebra. That means it has to come with a multiplication, and multiplication should be nice enough, and it should be close with that with respect to the norm. But additionally, it should have some involution. That means there should be a way of taking some kind of adjoints to each element. Okay, that means what is involution? Involution is a map from the vector space to itself, such that when you take the involution two times, it gives you the identity. That means if I denote the involution by star, then star of A star is equals to A. Okay, first condition. And second condition, this is how the second condition is the most powerful condition, and this actually distinguish all the star algebras. I mean, this distinguish C-star algebras from all other Banach algebras. That is, norm of A star A should be equal to norm of A whole square. Okay, this is a very good condition. I mean, one more thing is that suppose you have a C-star algebra or you have a star algebra, then I can ask you the question: can you uh, give me a norm on that norm on that algebra such that it becomes a C-star algebra? Okay, so first thing you have to note that if you define some norm on that C-star algebra, then it has to satisfy the second condition. Okay, and some results says that there exists precisely one way of getting such a norm on a given star algebra. Okay, so okay, so let me briefly describe some examples, some very familiar examples. Firstly, of course, the set of all n cross n square matrices, whose entries are taken from the complex numbers. Then of course, the set of all bounded operators on a Hilbert space H. These are very standard kind of sister algebras. Then there exists, let us discuss some non-trivial sister algebra, which is the set of all compact operators on a Hilbert space H. Now note that when I'm talking about sister algebra, then I'm saying that it comes with a multiplication. Now we can talk about the unit element of the algebra, right? So that means we can ask the question whether there exists a, multiplicative identity or not. The answer is it is not necessary. It is not necessary for all the sister algebras to have the multiplicative unit. But here in my talk, I will be assuming that all of the sister algebras are unital. That means it has some kind of multiplicative unit. But in general, sister algebras do not need to have a multiplicative unit. For example, in this example 3, the set of all compact operators on a Hilbert space H, it doesn't have a multiplicative identity when H is an infinite dimensional Hilbert space. Okay, because then the identity element will be the identity operator, and identity operator is not a compact operator for infinite dimensional Hilbert space. Okay. All right. Then the next, the most interesting Hilbert sister algebra is the commutative sister algebras. Okay, and this is C of X with a uniform norm, where X is a compact Hausdorff space. Okay. Yeah, and here the multiplication is defined by pointwise multiplication, and the adjoint is defined as adjoint is defined pointwise. That means, yeah, f star of x is nothing but f of x bar. Yeah. Okay. So next, I want to discuss some facts about maybe sister algebras. Okay. So plate A and B are two sister algebras. Then I want to define the, okay, so here till now I have discussed the objects of our study. The objects are sister algebras. Now, again, whenever we discuss some object in mathematics, then next thing we discuss are morphisms. So here our morphisms are star homomorphisms. Okay, so between two sister algebras, a star homomorphism is a linear map from A to B, which has these two properties. Firstly, it is self-adjoint. That means pi of x star is equals to pi x star for all x in A, and pi is multiplicative. Okay, so these are the two necessary conditions to become. I mean, firstly, pi has to be linear. Secondly, it has to be self-adjoint. Thirdly, it has to preserve the multiplication structure of the sister. Okay, of course, you see, sister algebra is not only about the algebraic structure or the involution structure. It also comes with some norm structure. Basically, it comes with some topology. But you see, there are some theorems that ensures that whenever there is a star homomorphism, that means it satisfies these two conditions, and if it sends the unit elements to unit elements, then it trivially becomes a bounded linear function. Okay, yeah, it is redundant. And okay, and the second thing I want to define is the spectrum of an element. Okay, for any element K in the sister algebra A, we can define the spectrum of A to be the set of all scalars lambda, such that A minus lambda is not invertible in the sister algebra K. Okay, so now we have already talked that sister algebra comes with a multiplicative structure. We have talked about the unit element. Now I have assumed that our all sister algebras are unital. That means it has some multiplicative unit. identity. So now we can ask whether if we are given an element A, does there exist an element B such that AB is equal to BA is equals to the identity element? Uh, the answer is for all the elements, there doesn't exist in there may not be existing some inverse of every element. So spectrum of A is the set of all scalars for which A minus lambda is not invertible. Okay. Now here are some set of definitions. Suppose A is any element in the C star algebra A, then we call A to be self-adjoint if A is equals to its adjoint, or equivalently you may say that spectrum of A is contained in the set of real numbers. Okay, basically spectrum of A is a subset in the complex field, but we say it is an element to be self-adjoint if if it is equal to its adjoint, or equivalently its spectrum is contained in the real life. Okay. Now, secondly, we call an element to be positive if its spectrum is contained in particularly in the positive side or non-negative side of the real line, or equivalently uh, if it is of the form B star B for some element B in the C star algebra A. Okay, that means for example, in case of complex number, the positive numbers are those numbers for which there exists, I mean, they can be written as some B star B, where B is another complex number, right? Yeah, so this is just the generalization of those ideas. And yeah, and thirdly, I say that an element to be normal if A star A is equals to A star for all. Okay, so here this is typo. I want to define what is normal element. So I say that an element A to be normal if it satisfies A star A is equals to A star. So ignore the for all part of it. Yeah. So
Hello.
yeah, yeah,
So these first two points are true only when A is normal.
yeah.
I mean,
Actually, so that's why I wanted to write the third point in the first, but yeah, somehow I assumed it already. Yeah,
okay.
yeah, yeah. I'm sorry for that. Yeah. So some quick facts. All right. So for every element in the C star algebra A, we can define the spectrum of A, and the spectrum of A is firstly non-empty, and secondly, it is a complex set for every element in the C star algebra. And in fact, it is contained in the uh, ball of radius norm of A around 0. Okay, what it says is that we want to see the set spectrum of A. Okay, and it is contained in the closed ball of radius norm A around 0. Okay, uh, it will be helpful in some deducing some facts which will come in the later part of the talk. Okay. All right. So this is the GNS representation kind of theorem. Suppose I have a C star algebra A, then there exists a Hilbert space H, and then isometric star homomorphism pi from A to BH, set of all bounded operators on H. Uh, yeah, so it means that if we okay, so if you note that we have defined the C star algebras very abstractly. Okay, these are basically very abstract things. But after some time, what we have got is like they are actually very concrete. So that means whenever we are given a C star algebra, then we can have some Hilbert space H, and we can think of those that C star algebra is a C star sub algebra that is contained in the nice C star algebra B of H. Okay. So actually, all the C-star algebras are very concrete. So whenever we study all the sub algebras of C-star sub algebras of B of X, then we are done. Okay. So here is what we call the commutative C-star algebra. A C-star algebra A is called commutative C-star algebra if the multiplication is basically commutative. Okay, and this is one important theorem that says that every commutative C-star algebra is isomorphic to C of X for some compact construct of space X. Okay. Yeah, here is one thing I wanted to mention. So there are many people here who are working in topology. So there is a fancy way of, denoting C-star algebras as non-commutative topology because of this fact. Okay, so you see every commutative C-star algebra, they look like C of X for some compact Hausdorff space X. All right. Now, various topological properties on X can be translated into some C-star algebraic property of C of X. Okay. For example, X is connected if and only if there exists no non-trivial idempotent in C of X. Okay. So there exists a kind of duality between the C-star algebra structure of C of X and the topological space X. Okay, so that's why people call C-star algebra as a theory of non-commutative topology. Okay, so now we want to define something new, and this is called operator system. Okay, all right. So the operator system is a vector subspace of a C-star algebra A. Okay. Additionally, it should have two properties. Firstly, it is self-adjoint, and secondly, it should contain the identity element. Okay. What I mean by that is the following. Okay. Firstly, it has to be a vector subspace of the C-star algebra. Secondly, if A belongs to the operator system S, then A star belongs to the operator system S. Okay. Secondly, it has to contain the identity element of the operator system S. Some books actually says that it should be closed under the norm of the C-star algebra, but here in our discussion we don't need that assumption, so I will skip that. Okay, we basically need these two properties. All right, now note that whenever, suppose I have a operator system S, and suppose small a be any element of the operator system S. Okay, then I can write A as a linear combination of these two elements. Okay, you note that these two elements, A plus A star divided by 2 and A minus A star divided by 2i. Okay, these two elements are self-adjoint. Okay, so what does it mean? It means that any operator system is spun by the self-adjoint elements of the operator system. Okay, that means in the operator system there are enough self-adjoint elements to generate the whole operator system. Okay, now again, suppose X is any self-adjoint element, then I can write it as like the span of two positive elements. Okay, I mean linear combination of two positive elements. Okay, so here I can write X as norm of X plus X divided by 2 minus norm of X minus X divided by 2. Okay, yeah, so this is a kind of good thing. Yeah, so here you have to note that whenever you are given a self-adjoint element X, then X plus minus norm of X is always greater than 0. That means it is always positive. Okay. So the conclusion is that any operator system is actually generated by its positive elements. Okay. So we can conclude that whenever we are given an operator system, there exist enough positive elements to generate the whole operator system. Okay. Now we are in a position to define positive maps. Okay, you see, now we have the notion of operator system. Okay, initially we were dealing with C-star algebras. Now operator systems are some objects. I mean, operator systems are some vector subspace contained in some C-star algebras. Now, uh, in operator system, we have more flexibilities because it doesn't have much structures as compared to the C-star algebras, but the operator system do have some structures related to positive elements. So we can talk about maps which preserve this positiveness. Okay. Okay. So that's why I want to define positive maps. A positive map is a linear map from an operator system to some C-star algebra V, such that the image of every positive element is positive. Okay. Now see here, S is an operator system, B is a C-star algebra. Now I can talk about positive elements in S and positive elements in B. Okay. Now I say that a linear map is positive if it takes positive elements to the positive elements of B. Okay. Yeah. All right. So now I wanted to discuss something new, right? Not new, I mean, which was not discussed in our operator theory course.
One question. So
Yeah.
these positive maps are not star homomorphisms.
No, yeah, these
Okay.
are not necessarily, because it doesn't say anything about multiplicative structures, you know. And for example, you see the operator system, when we
But we
define
can still require that phi of A star is phi A star.
it will become okay. Yeah, phi of A star will become. I mean, that property will hold for any positive map actually. So if a map is positive, then it will preserve the star property. Okay, that means it will be a self-adjoint map. That means
So
if
it's a
E is
consequence,
positive,
you're saying.
yeah, it is a consequence, but it will not preserve the multiplication.
Yeah, because there's no
Yeah.
multiplication in S. Okay.
Yeah, yeah.
Okay. Thanks.
For example, any measure, you say any measure, action of any measure on C of X, provided it is not Dirac measure. Yeah. Okay. So C-star algebra actually comes with some hidden information. Okay. Suppose here we assume that S is an operator system contained in the C-star algebra A. Okay. Now for each natural number n, I want to define Mn of A. Okay. This is a set of all n cross n square matrices where each element of the matrices are coming from the C-star algebra A. Okay. Now I will stress on this point. I will spend some time here to dissolve this idea. Okay. Now we already have an C-star algebra A. Now for every natural number, I want to define Mn of A. This is the set of all n cross n square matrices whose each entries are coming from a C-star algebra A. Okay. Now what we have found, I mean not we have, I mean what mathematicians have found is that this Mn of A is actually a C-star algebra for all n greater than 1. Okay. That means whenever you are given a C-star algebra A, then for each level n, you can construct some new C-star algebras. Okay. Now, okay. So suppose I'm given a C-star algebra A. Now I have said that Mn of A is again a C-star algebra. Now the question is, what is a norm on that level? Okay. Now you see, I have already said that every C-star algebra can be thought of as a C-star subalgebra of B of H. I mean, set of all bounded operators on some Hilbert space. Now, imagine these elements of these A are some operators. Now, what is Mn of A then? It is some n cross n square matrices whose each elements are coming up from some B of H, okay, where H is same for all, of course, all the entries. Now then, this n cross n square matrix is actually a bounded linear operator on the direct sum of n copies of that Hilbert space. Okay, so basically it inherits a norm structure very naturally. So I just didn't want to go to the details of that thing, but the norm structure in Mn of A comes very naturally. Okay. Yeah. So Mn of A is a C-star algebra for all natural number n. All right. Now, what about the operator system S? In fact, I can define Mn of S for the operator system S also. So Mn of S is nothing but the set of all n cross n square matrices whose each entries are coming from the operator system S. Okay. Now, but we know that Mn of S is an operator system contained in the C-star algebra Mn of A. So initially we were given the operator system S contained in the C-star algebra A. Then what we have found that for each natural number n, Mn of S is an operator system contained in the C-star algebra Mn of A. Okay. All right. Now suppose I am given a linear map P from the C-star algebra A to B. Okay. Now the question is, can we lift this map on each level? The answer is yes, and this can be lifted to each level very naturally. What is the definition then? Suppose P is any map which is linear from A to B, then we can define a linear map Pn from Mn of S to Mn of B as Pn of this matrix should be a matrix in Mn of B whose Iz entry will be P of Aiz. Okay. So this is a very natural definition. That means the moral of the story is whenever I'm given a linear map P from on the level 1, then I can have linear maps on each levels. Okay. Now we can talk about completely positive maps. Okay. Suppose I have a linear map P from a operator system X to a C-star algebra B, then we can say that it is completely positive if the new maps Pn is positive for each n. Okay, so I wanted to write here Pn is positive for each n, that then we call it to be completely positive map. Okay. Moreover, if the map takes the identity element to the identity element of B, then we say that it is unital completely positive map. That means it preserves the unit and it is completely positive. Then we call it unital completely positive map. And in short, we say this to be UCP map. Okay, and these are the central objects we are working on, and I'm working on. Yeah. Okay. So here are some examples. Okay. Suppose. All right. Here, one thing you should note that I have defined unital completely positive maps for operator system only. Okay, we don't need to have a C-star algebra to define unital completely positive maps. Okay, of course, any C-star algebra is of again operator system, so I can talk about the UCB maps on a C-star algebra. Now let when we are two C-star algebras and P is any positive map. Okay, now okay, so here is the thing. Now suppose I have a map P from A to B. Suppose it is positive, but it will not mean that it will completely positive, because complete positivity is a very strong class of maps. Okay, it requires a lot to be a completely positive map. So there exists some map which are positive but not completely positive. Okay, right now I won't give you any examples. I mean, they are not very I would say easy to construct, but yeah, but I must stress that there exist some positive maps which are not completely positive. Okay, but we can ask the question, when can the positive maps be completely positive? In some special cases, that is actually true. I mean, in some special cases, positivity will imply the complete positivity of the map. Okay. For example, suppose phi is any positive map between two C-star algebras A and B. Okay. If any one of the domain or the codomain is commutative, then positivity will imply complete positivity of the map. Okay. For example, suppose our C-star algebra A is commutative C-star algebra C of X for some topological compact Hausdorff topological space X, and our codomain is C, and it is suppose a measure, then it is a measure, right? Positive measure. Then we can show that it is actually a completely positive map. Okay? It means it is positive. Mu n is positive on each level. All right. Now, Tejasvi has just asked one interesting question, that uh, what is the difference between the positive maps and star homomorphisms? Okay. I have said that not all positive maps are star homomorphisms, but all the star homomorphisms are positive maps. In fact, all the star homomorphisms are completely positive maps. Okay. For example, let pi be a map from a C-star algebra A to B, and suppose it is a star homomorphism, then in particular it is a positive map. Okay, we can show that. Now we can also verify, it is a very easy calculation, that pi n on each level, pi n I can define on mn of A to mn of B. Then on each level, pi n is again a star homomorphism if we start with pi to be a star homomorphism. Okay, then on each level it is a star homomorphism. So we know that whenever it is a star homomorphism, it is a positive map. So that means pi n is again positive for all n, and that's why pi is actually completely positive. Okay, so whenever we are given a star homomorphism, then it is a positive map. In fact, it is a completely positive map. All right. Here is an interesting example, and this example is very important for context. Now, suppose H and K are two Hilbert spaces such that the Hilbert space H is contained in the Hilbert space K. Okay. Now let V is an isometry from H to K, the smaller Hilbert space to the bigger Hilbert space. Suppose V is an isometry. All right. Now let pi be a star homomorphism. That means pi is a C-star algebra representation from the C-star algebra A to the B of K, where K was the bigger Hilbert space. Okay, suppose pi be a star homomorphism. Then I'm defining a new map from A to B of H, and I name it to be small p. And I want to define it as the compression of the map pi by the isometry B. Okay, I will discuss the notion. Okay, now for example, you see pi is a map from A to B of K. K is a Hilbert space. Okay, so for any A in the C-star algebra A, pi of A is an element in B of K, right? Now I want to view this pi of A as a operator acting on the smaller Hilbert space H. And for that, I will take the help of an isometry V. Okay, now that is how I define the new map. So phi of A is the compression by V star phi of A V. And I mean, we can look this map like this. Actually, when we identify H as a subspace containing the Hilbert space K, then this map is actually like this. So phi of A, it takes elements from the Hilbert space H, and it will give you an element in the Hilbert space K. I mean, it will be an element, give you an element in the Hilbert space K, and now you can project it on the Hilbert space H. Okay. Now we can verify that maps like this are also completely positive. Okay. But the next thing I want to discuss is very interesting. It is called Stieness-Spring dilation theorem. And whenever you hear something about unital completely positive map, then you will hear about Stieness-Spring dilation theorem. It's like music; it will come together. Okay. So what it actually says that, note that we have discussed some classes of unital completely positive maps, and the third example actually generalizes the idea of uh, example 2. Okay, in the example 2, we have discussed that every star homomorphisms are actually UCP map. In the third example, we have taken the help of star homomorphism to define a new class of uh, UCP map. Now, fourth question we may ask is how different these UCP maps are from the star homomorphisms. Okay, now this dilation theorem gives you the answer. Okay, now what it says. Okay, let us discuss this theorem. Suppose phi be any UCP map from the C-star algebra A to B of H. Then this theorem says that there exists a Hilbert space K containing the Hilbert space H and an isometry V from H to K and a star homomorphism phi from A to B of K such that phi of A is nothing but the compression of the star homomorphism phi of A. Okay, so what it says is that these UCP maps are not very different from the star homomorphisms. Okay, yeah. So this is a good thing, and it actually generalizes the idea of GNS representation theorem. Okay, for example, here. So what was GNS representation theorem? Suppose A is any C-star algebra and P from A to C be any UCP map. Okay, so here I mean, whenever A is a C-star algebra and the codomain is complex numbers, then UCP maps are same as states. Okay. Then for every state phi, I can construct the GNS representation pi phi of the C-star algebra A, and that is nothing but the Stieness-Spring dilation of the UCP map phi actually. Okay. In fact, this is the minimal kind of dilation of this UCP map phi. Okay, let's not go into that. But here I just wanted to stress that UCP maps are not so bad. They are very similar to star representation whenever the codomain is B of H. Okay. Yeah, so this idea of dilation has a separate theory. I mean, that is a different domain of study. It is called the theory of that is the dilation theory. Yeah, so I use a lot of tools from dilation theory in my work. Yeah, so dilation theorem is actually the generalization of genus representation theorem. Okay, so here I wanted to give some examples. Okay, so In topology, what we did was like we defined some manifold very abstractly, and we proved that every manifold actually can be embedded in some Rn completely. Okay. Now I have defined what is operator system here. You see, operator system, I'm defining it to be very concrete. Okay, it is contained in some sister algebra, I'm saying. But there are some definitions which are more axiomatic. Okay, that means we can define operator system very abstract sense, and then we can prove that every operator system can be realized as an operator system contained in some sister algebra. Okay, that is one point I wanted to say. All right, now, so I mean, it is easy to see that if we are given a operator system S, then there can be multiple sister algebra in which we can embed those objects. Okay. For example, let B be the set, B be the open unit disk on the complex plane. Okay. Now D bar is the closure of that thing. A D bar is a collection of all functions defined on D such that either F is holomorphic or F bar is holomorphic. Okay. And second condition is F is continuous on the boundary. Okay. Now it is easy to see that A of D bar is actually a operator system. Now I can have two different C-star algebra containing containing the same operator system. Firstly, A D bar is contained in C D bar, set of all continuous functions on D bar, and A D bar can be thought of as a operator system contained in the C-star algebra C of T, okay, C of the circle, continuous functions on the unit circle. Here, for the second inclusion, we can use the maximum modulus principle kind of thing to give an isometric kind of thing. Okay. Yeah. So, but the thing is, okay, first let us check the first containment. Okay. Now A D bar, I have said that A D bar is contained in the C-star algebra C D bar. Now I can ask the question, what is the smallest C-star algebra contained in C of D bar that contains A D bar? The answer is C of D bar itself. Okay. And in the second case also, we can ask the question, what is the smallest C-star algebra contained in C of T that contains the operator system A of B bar? The answer is C of T. Okay. So in a sense, the minimal C-star algebra containing a operator system is not so well defined in this sense. Okay, they are not unique kind of thing, but we do have some minimal embedding kind of thing, but they are defined using some universal properties. Okay, then we have the notion of Sylow boundaries and all, yeah, those things. Okay, I wanted to discuss this thing for a reason. Okay, now I want to come up with convexity. Okay. Okay. Suppose we are given an operator system, then I want to define something that is called state space of an operator system. Okay. Now suppose suppose S is an operator system contained in some sister algebra A such that the A is the smallest sister algebra generated by the operator system S in the sister algebra. Okay. Yeah. So let S be the collection of all states. That means the UCP maps. Okay. Whenever I'm saying states, that means UCP maps P from the operator system S to complex plane. Okay. So that means S be the collection of all states P from the operator system S to see. For example, if we replace this S by C of X, some commutative C star algebra C of X, then the state space will be the set of all probability measures. Okay. Yeah. Then the following are true. You see, every element of state space is a linear map. Okay. In fact, they are continuous linear map. So these are actually contained in the dual space of the operator system S. Okay. Secondly, it is a convex set. Why it is a convex set? I mean, you can take the convex combination of two UCP maps, and you will get a UCP map. UCP map. Okay, so it is a convex set. Thirdly, it is a complex set with respect to the weak star topology in the dual space. Okay, so this state space is actually a very nice space. I mean, this is a topological space, of course, but it is compact, Hausdorff, and convex. Okay, and this convexity is going to be very powerful in the later part of the talk. Okay. So from now I want to go through some chronology here from operator theory, operator system to convexity. Okay. Now let us start. Let us begin with an operator system S. Then we associate a convex set K, which is very special, which is the set of all states on the operator system S. Then what we know now is that K is a compact convex Hausdorff topological space. Okay. Now once we know that the set is convex, then I can talk about many things. For example, affine functions, secondly, convex functions, concave functions, and so on. Okay. For example, I denote by AK, I denote the set of all affine maps defined on the set K. By affine map, I'm meaning that f is a if f is a function from K to C, and if it satisfies this equality, that means if it respects the convexity of K, then we say that f is an affine function. Okay, then I denote the set of all affine functions by K of K. All right. Now, all right. Now, what we have till now is that we start with an operator system S. We have associated a convex set K, which is the state space of S. I denote AK by I denote the set of all affine functions by AK. Secondly, for each element of the operator system S, I want to define an element K bar, which is a function from K to C. Okay, how I want to define? I define it by K bar of K is defined as K of A. You see, this K was nothing but set of all UCP maps defined on the operator system S. So this K of A makes sense. Okay, now that's why I can talk about K bar, and I can define A bar like this. Okay, so that means, and you can also verify that for every A, this A bar defined like this is actually a affine function defined on the convex set K. Okay, so I want to stress this thing. For every A in the operator system S, K bar, that is a function defined on K like this, is a affine function. Okay, so that's how we get a map capital Phi from the operator system S to A of K, set of all affine functions on K. Now, and the map is sending A to the A bar, A hat. Okay. Now note one thing. Here S is operator system. A of K is a set of all affine functions. Now you can show that this is actually an operator system contained in the C-star algebras, all continuous functions on K. Okay. Now, what is the beautiful theorem? The theorem says that this map P is actually bijection. Secondly, it is a positive map. Thirdly, it is a isometric map. Okay, that means capital Phi is a complete isometric isomorphism. Okay, that means now this operator system S and the new operator system AK, they are same as operator system. Okay, now why this theorem is important? Now you see, I have started with a very abstract kind of operator system, and now we have a very concrete operator system of all affine functions on a given convex K. Now I have all the technologies of convexity to discuss the properties of AK and deduce some relevant properties in S. Okay, so I mean, if we want to study the operator system, it is enough to study the set of all affine functions on a convex K. Okay, yeah. I mean, K is even more powerful in the context of C-star algebra. So I will discuss that thing. All right. Suppose A is any C-star algebra which is commutative. Now we know that every commutative C-star algebra is of the form C of X. Okay. Now suppose S is an operator system contained in this C-star algebra C of X. All right. Now what we have, I have a operator system contained in the C-star algebra C of X. Now again, I can construct some convex set K by this procedure. All right. Then I can talk about A of K. Okay. Now since A of K is isomorphic to the operator system S, now that means what? I can embed the same operator system in C of K. Okay. Now question is, does there exist any relation between the old C-star algebra C of X and the new C-star algebra C of K? The answer is yes. Okay. So whenever K is any commutative C-star algebra such that the C-star, the C-star algebra generated by this operator system is A, that means the whole C-star algebra, then there exists a surjective star homomorphism pi from Ck to Cx such that pi AK, when we restrict the map, restrict the star homomorphism on the set of all affine functions, that will be an inverse of the function, inverse of this function, this map. Okay, capital P. Okay, so I mean, that thing is the point 3 is not necessary for this talk, but it makes the set K very powerful. Okay, all right. So extension of QCP maps. I will not take much time from here. I will quickly go through some definitions. Extension of Arveson's extension theorem. Okay. Suppose I have a QCP map Phi from the operator system S to B of H. Okay. Now the question is, suppose A is a C-star algebra containing the operator system. The question is, can we extend this UCP map to a UCP map defined on the whole C-star algebra? The answer is yes, and Arveson gave a proof of this theorem, and he said that whenever I'm given a UCP map Phi from operator system S to B of H, then I can define a map capital Phi, which is an extension of this map. So you see, I want to stress one more thing here. For first glance, it will look like that it is a theorem about operator system and the C-star algebra containing it. Okay, but it is a theorem about the codomain also. See, I'm strictly fixing the codomain here. I'm not writing any arbitrary C-star algebra on the codomain. I'm saying the codomain must be B of H. Okay. Suppose I'm imposing some. I'm not imposing B of H on the codomain. I'm giving some abstract C-star algebra B on the codomain. Then we may ask the same question. Whenever we are given a UCP map P from an operator system S to a C-star algebra B, can we extend this map to a UCP map capital P from the C-star algebra A to the C-star algebra B? Answer is not always. And whenever we then the notion of injectivity comes into the picture, and maybe we can discuss that on another day. But yeah, so here we must note that here the codomain is very special. Yeah, so again, here you see each of this map can be extended to a UCP map on the whole C-star algebra. That's right. But this theorem is not saying anything about uniqueness. The question is, suppose I know now that every UCP map on a operator system can be extended to a UCP map on the embedded C-star algebra. The question is, can we extend this UCP map uniquely? Answer is no. Okay, not always. So it is interesting to study those cases where the extensions are unique, and I am working on precisely this setting. Okay, there are many conjectures regarding these concepts, and my work is closely related with Arnison's hyperrigidity conjecture, which deals with the unique extension property of unital completely maps. Okay, now unique extension property of these maps has a very deep connection with approximation theory in appropriate context. So, yeah. All right. Now I want to define unique extension property. Okay, so unique extension property is defined for start. Okay, so who are the participants for this property? Answer is the star homomorphism of a C-star algebra are the participants for this property. Okay, we say that a star homomorphism P star homomorphism pi from a C-star algebra A to B of H has the unique extension property if whenever capital P is any other UCP map from A to B of H such that they are equal on the operator system S, then that will imply that globally they are equal. Okay, so unique extension property is defined with respect to some operator system. Okay, so here the context of operator system comes into the play. Okay, so we say that when star homomorphism pi has the unique extension property if its restriction to that operator system has unique extension to the whole C-star algebra, and that should be pi itself. Okay. Yeah. Okay. Now I'm again going back to the convexity for a reason. Okay. Now you see, suppose I have a operator system C contained in the commutative C-star algebra C of X. You see here I already have a topological space X. So more or less this operator system is very concrete and very beautiful. Then again from previous construction, we have some kind of C of K, or the convex. Now we have the convex set K, the set of all affine functions on K, and set of all continuous functions on K. Now, why this K is more important than X? Answer is because in general, X is not taken to be convex, but K is convex. So K is very important even if it is coming from a commutative system. Okay, all right. Suppose some operator system S is contained in the C-star algebra C of X, then we know that this S is same as set of all affine functions A of K on K. Now we also know that there is some star homomorphism which is very nice from C of K to C of X. Okay, we know that we can construct a map like this, and I don't know who actually discovered this map. Okay, yeah. Anyway, okay. So it should be, it shouldn't be 8. It should be a star homomorphism. Okay. So all right. So I want to classify all the star homomorphism defined on this C star algebra C of x, which has a unique extension property with respect to the operator system S. Now, this convexity theory gives us a way to classify all those star homomorphism, which has the unique extension property with respect to any operator system contained in the C star algebra. Okay, how? Suppose phi be any star homomorphism, so read it as star homomorphism. Okay, phi be any star homomorphism which has unique extension property with respect to the operator system S, if and only if phi composition Q, which is a star, which will be a star homomorphism from C of K to B of H, has the unique extension property with respect to the operator system A of K. Now, look closely. I have two setups. One on left, I have S contained in C of K. On right, I have some C of K, and it is containing A of K. Now I can talk about unique extension property of some. I mean, pi, this map pi has unique extension property with respect to the operator system S, if and only if its pullback to C of K has the unique extension property with respect to A of K. Okay. All right. Now that means our problem is reduced to classify all the star homomorphism of C of K for K convex, which has the unique extension property. Okay. All right. Now I want to classify all the star homomorphisms of C of K, which is the star homomorphism, which has the unique extension property where K is particularly good. That means K is convex. All right. Note that any representation can actually be written as a direct sum of cyclic representations. Okay. Now, it is very easy to see that this new representation pi compose Q has unique extension property if and only if each of its constituent cyclic representation has the unique extension property. Okay. That is not very difficult to see. Okay. Now, cyclic representations of commutative C star algebra are very nice actually. How is that? So there is a very nice one-to-one correspondence between cyclic representations of C of K and the probability measures on K. That means for every cyclic representation, sigma mu can be written, I mean, every cyclic representation of C of K can be written as sigma mu for some probability measure mu. Okay. Now, actually, this sigma mu is nothing but the GNS representation of the state mu. And now mu is a probability measure. I can view mu as a linear, positive linear functional on C of K, right? So I can talk about its GNS representation. Actually, this any cyclic representation is coming out of a probability measure as a GNS representation of that measure. Okay. That is very that is not difficult to see once we know what is GNS representation. Okay, so what I mean by this theorem is that there is a very nice and natural one-to-one correspondence between the cyclic representations and the measures of the convexity K. Okay. Now, what we can conclude here is that the problem of unique extension property in the commutative case has become a problem of measure theory in a compact convexity. And these, this theory is called the Chopin theory, classical Chopin theory. it deals with the convexity and the set of all probability measures on the convexity. Okay. Now we started with the representation of the commutative sister algebra. We asked the question of unique extension property of some very abstract topological space X and some very abstract Hilbert space H. Now what we are now we are on a point where all the problems are reduced to some problems of measures of convex sets, convexity K. Okay. Now I have all the technologies to answer. I mean, we have all the technologies like convexity, theory of convex functions, theory of affine functions, theory of concave functions to answer this kind of questions. Okay. Uh, so that's how convexity comes into the play in my study. All right. But these things are already done by some legends. Our question is, do we have some similar theory to discuss unique extension property in non-commutative case? That means in the commutative case, we have some nice correspondence between measures and unique extension property. Now, can we do some similar treatment in the non-commutative scenario? And this question brings us to the realm of non-commutative Choquet theory. That means we can talk about non-commutative sets, non-commutative UCP maps, and many more things, non-commutative. Okay, so whenever I'm talking about convex sets, I can talk about extreme points, right? Now I'll be talking about some non-commutative sets, then I can talk about non-commutative extreme points. And these have some very beautiful consequences in the theory of C-star algebra and operator system. So yeah, so I don't have much to say, basically. Thanks for listening. And if you have any questions or comments, you are very much welcome. Yeah, thank you for listening.